Hello again. Welcome to the last talk of today from Corentin Bayet and Journey to Freedom. Enjoy.
Hi everyone, thank you for being here on this last talk and to join us in our journey to freedom. So I'm Corentin Bayet, I'm a security researcher at Reverse Tactics. We are a French company doing mostly VR and reverse engineering. And I did this work with Bruno Pujos, he's still also here, but I will talk alone today. And he's a CEO and founder of Reverse Tactics. This talk is about the chain we used at Point2 in Vancouver 2024, so last year, where we escaped from VirtualBox and then used the local privilege escalation on the Windows host. So today we only have time to talk about the first part. That's why I'm talking alone. So about Point2, Point2 is a hacking contest organized by ZDI. I'm sure everybody knows about it. Last year it was in Vancouver, but this year it's happening right now at OffensiveCon. And Point2 has a virtualization category where you have to demonstrate virtual machine escape using 0-day. Yes, there is multiple targets like VMware Workstation, ESXi, Hyper-V, and VirtualBox. And your goal is to start with administrator or root privileges in the guest, which can be Linux or Windows, and you must demonstrate arbitrary code execution on the host. And for the type 2 hypervisors, like VirtualBox or Workstation, you can also chain it with local privilege escalation on the Windows, targeting the kernel, because most of the time when you escape, you will target the userland process, so you will end up with code execution in userland. And quick word about the configuration. The configuration of virtual machine, you can have a lot of them. And yes, it has a huge impact on the attack surface because we will usually enable some specific hardware or devices that will be exposed to the guest. So you don't have to target the default configuration for the contest. There is no such thing as a default configuration actually. But yeah, your configuration must represent something that is valid, realistic, and you just ask the DI and they will tell you if you can enable this device or not. So yeah, we'll start with a few definitions and a few reminders about virtualization and how we're working setup. And so VirtualBox is a very popular hypervisor. Maybe lots of you know them. You know it because it's open source, it's free, it's really easy to use, and it's working on most major operating systems, so Windows, Linux, Mac OS. It's maintained by Oracle. I'm quite sure they don't make any profit on this product, so they have no team 100% dedicated on VirtualBox security. So yeah. And a few definitions before starting. So an hypervisor is a software that manages one or multiple virtual machines on a single physical computer. In our case, it's VirtualBox. The host is the operating system running the hypervisor. In our case, it's Windows. The guest is the operating system running inside the virtual machine. We use Linux, but we can also use Windows. And two small definitions we will use a lot in this talk is GPA, or guest physical address, which is an address in the physical memory view of the guest. So the guest thinks it's actual raw memory, but it's not, it's virtualized. And paravirtualization is a virtualization technique where you modify the guest OS, you develop specific interfaces to be able to communicate from the guest to the host. And you provide drivers, we provide mostly drivers to the guest, so you can communicate directly with the hypervisor, sorry. And the goal is to improve mostly performance for costly operation like network cards or disks, or to add some features, for example, shared folders or copy paste or things like that. Sorry, it's mostly paravirtualization. And finally, I want to speak about the communication channel that you have between the guest and the host. So the guest actually thinks it's communicating with hardware, so it's using the same mechanism. So it's mostly through physical memory, which can be seen as DMA when you talk to hardware. And then you can trigger specific action through two similar mechanisms, which are PMIO and MMIO. It's basically the same. With PMIO, you trigger it with specific privilege instructions, which are in and out instruction in the x86 instruction set. And MMIO is memory mapped IO, so you just have to read or write in specific physical memory ranges, and it triggers the VM exit that the hypervisor has to handle. And finally, there's hypercalls. It's, again, specific interfaces. You can view them as like syscalls, but from the guest to the host. And yeah, it's mostly used for power virtualized devices. And yeah, that's it. And finally, I want to talk a bit about my setup. When I'm doing VR on hypervisors, I'm mostly using chipsec, which is a framework that was developed for testing the security of hardware or system firmwares. And chipsec already developed drivers for Windows and Linux that exposes a lot of privileged operation to the user land, like allocate, read and write in physical memory, execute privileged instructions like in or out or hypercalls, or read or write in PCI device and everything. And it has a Python API, so it's operating system agnostic, and you can just write Python. And for example, I have this snippet of code. I just initialize chipset, load the driver and everything, and then I can use Python to read-write into physical memory, to read-write into MMIO or anything else. So it's really convenient, and I'm mostly using this when I'm doing VR. And yeah, let's start with the actual research. So a good journey always starts with a good state of the art. For me, it's a very, very important step that you cannot neglect. So you have to put time into it because it will save you a lot of time later. And the goals are mostly to find a lot of information on the target, like the documentation, if is it fuzz, how is it fuzz and everything. And of course, to also study previous vulnerabilities, to understand the attack surfaces, to know the exploit techniques, and most importantly, to extract the vulnerable patterns, which are the kind of bugs that you can find in the code base and that you might re-find. And while doing this, I studied this bug, which is an uninitialized memory read in VirtualBox that was found and exploited by Major Tom Sek, a former colleague from Synactive, that he used it for Point2 in 2023, so 2 years ago. And the bug was affecting a function called PGM freeze read, which is a function you find everywhere in the code base because it's the function responsible for reading the physical memory of the guest to a host buffer. So you can really view it as a mem copy or a copy from user if you're more used to the Linux kernel, for example. And the source address is a GPA, and then you have a host buffer on the size, basically. And this function does two main things. First, it must split the access page by page, because the physical memory is not supposed to be contiguous. So it has to split the access page by page, because each page can be located in a different place in the host memory. And the second thing it's doing, it also has to handle MMU accesses, because one of the page can be registered as a specific memory range that must trigger an action. So if it's the case, sorry, it must call the appropriate MMU handler. So this is an extract of the function, really simplified. So it takes a physical address and buffer on a size, basically. And it loops on each page. It computes the size for the current page, and then there's a check to know if it's a MMIO handler, and if it is, it calls this function, PGM fills with handler, to call it. It's supposed to fill the buffer. And there's a specific error case, like if the handler fails for some reason, the function will try to leave early. And before doing that, it will try to initialize the buffer and leave. The issue there is that they're not using the correct size in the mem set. They're using CB, which is the size of the current page, but it's not CB read, which is the size of the buffer. So if you call this function with, like, you're supposed to read 10 pages, and the read on the first page is the MMIO handler that fails, it will return with 9 pages in the buffer that are not initialized. So Major Tom Sek found this in 2023, and it allows to let some data initialize when you're reading some data from the guest memory. And the only thing to trigger it is to be able to control the GPA that is provided to this function, which is a very, very common thing to find, because usually you will provide a GPA to the host and it will read from it. But what's more rare to find is that a code that will read some memory from the guest and then write it back, so we can actually read this uninitialized data. And Major Tom Sek did the work and found it is a XHCI device at the time. XHCI is a fancy name for the USB 3.0 interface. And yeah, this bug, so it allowed to leak some uninitialized memory from the host and get some stack and heap pointers and defeat ASLR. Sorry. So yeah, I was looking at this bug, and they patched it, obviously, after 2023, and this patch was quite straightforward. They just changed CB to CB read. And from that, I knew there was a vulnerable pattern. I knew that if this function, pgm_read, does not return a fully initialized buffer, there was a bug. So I just wondered what's happening in this function. And basically, this function is supposed to call the appropriate MMIO handler for the given GPA. And there is a lot of different MMIO handlers, because there's a lot of different devices that uses MMIO. And the MMIO handler is supposed to fill the provided buffer given on the GPA and the size and everything. And the question is, are they all doing it properly? And absolutely not. You have, for example, this MMIO handler for the bus logic device, which is a hard disk technology. And it does basically nothing, it just returns a success. So if you go back to the parent function, pvbuff is still not initialized. The function is success, so it will not trigger the memset pass, and you still have an initialized buffer. So just like that, in a few days, found a variant of the same bug in 2023. I don't even have to find an exploit technique because I can just reuse what Major Tomsek used in 2023. I just need to find a specific MMIO read handler that does not fully initialize the buffer and return a success. A small detail is that the MMIO handler has to be declared with a specific flag, which is called flags read pass-through. This is because normally MMIO handlers will only be called with small sizes like 1, 2, or 4. Except if they're declared with this flag and can be called with any size. So the MMIO handler for the bus logic device fits perfectly, and using this, we can already leak the content of the XHCI thread stack frame. From it, we can leak some stack pointers so we know where the stack is located. We can leak some text pointers so we can build web gadgets and everything. And we can also put some control data in this stack, so we can put some control data to known address in the host memory. So yeah, I found quickly a first bug, but it was time to start exploring with the ocean. And it's a good analogy actually because hypervisors have a huge code base and you can't really take the time to audit everything completely. It's very time consuming to fully understand an attack surface from top to bottom. And we clearly don't have this time. So the goal was to use all the knowledge acquired during the state of the art to quickly find other bugs like we just did. And to find some specific attack surfaces. You can obviously use tools. I mostly use grep, but some smarter guys might use CodeQL or things like that. And the goal is to find a list of things to look at deeper, and like low quality code or something else. And unfortunately, it was not a great success on virtual code base because I've mostly found too much false positive, which were too time consuming to rule out. A lot of vulnerabilities accessible only in the weirdest configurations that I could not use for the contest, or just non-reachable bugs or non-exploitable bugs. So yeah, I spent like 2 or 3 weeks reaching for those without finding anything I could exploit. But it still allowed me to explore a lot of different code and acquire knowledge on the code base, so I just decided to switch to pick an attack surface and look at it from top to bottom. And I decided to choose the VirtIO device implementation. So VirtIO is a specification for para-virtualized device, sorry. It was, I think, originally written for QEMU VM, but it's an open source implementation, so it's implemented now in a lot of hypervisors. And VirtualBox uses this specification to implement two devices, one VirtIO disk and one VirtIO network card. And that's cool about VirtIO is like you can compare the source code between like the QEMU implementation, for example, and the VirtualBox implementation. And the code of VirtualBox felt a bit weird. For example, we could find this kind of code where you have this defined. If it's defined, it will allocate the structure of a QBuff on the stack, and if it's not, it will allocate it on the heap. So I already find this quite weird. Don't know why you will do this. But what's weirder already, that's in this specific part of the code. Like if the define was set, then it was on the heap, and if it was not, it was also on the heap. So I decided to just go on this and understand everything that was going on there. And this is actually the code of the VirtIO queues. VirtIO queues is part of VirtIO, and it's a mechanism to send and receive data from the guest. It's implemented in the core of VirtIO, and thus it is used by all VirtIO devices. And what you want to solve with that is to be able to send a lot of data between the guest and the host. And the very common way to do this, not only in VirtIO, but is to use a queue of segment descriptors, because you cannot use just a single contiguous buffer of physical memory, because physical memory is not supposed to be contiguous. So usually you have a queue of segment descriptor where each segment will represent a chunk, like maybe a page or a few pages of contiguous physical memory. And you have each segment that is described by a guest physical address and a size. So basically, in VirtIO, the segment descriptor looks like this. You have 16 bytes, 8 for the GPA, 4 for the size, and 4 for some flags. You have 2 important flags. The next flags, which means if it's set that the descriptor chain is not over, and you have another descriptor to read after that, and it will be at the index n index, which are the last 2 bytes of the structure. And the write flag, if it's set, the buffer must be used for writing. If it's not set, it must be used for reading. Quite simple. So a descriptor chain looks like this. You have a first descriptor. The next flag is set, so we'll read the index there to get the next one, and you will do this until you find the descriptor where the next flag is not set. So yeah, I wanted to focus on this specific part in VirtualBox because it felt a bit weird. And in VirtualBox, it's implemented in this function. I will not say its name, but yeah, it's right there. And so the goal of this function is to parse the descriptor chain we just saw and to output in a VirtuBef structure. There's a lot of things in this structure, but the main things are these 2 lists of segment descriptor. You can see there's like the in list for write buffer and an out list for the read buffers. And you can see that the 2 lists have a fixed size of 1024. And each segment is described again by a GPA and a size. This is the implementation of the function. It's quite straightforward. You have a loop. At each start of the loop, it will read a descriptor from the chain. If the write flag is set, it will copy it in the in list. If it's not set, it will copy it on the out list. It will copy the GPA and the size, and it will loop until it finds a descriptor where the next flag is not set. So it's quite straightforward. So with some schematics, it looks like this. You have a first descriptor. The next flag is set, and the write flag is set, so it puts it in the in list. The next flag is set, so it goes to the next descriptor. The write flag is not set, so it puts it in the out list. Blah, 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 until you find a descriptor where the next flag is not set. Of course, you have an error stop condition, because you won't do this indefinitely. And this condition just counts the number of in segments and the number of out segments and compare it to the queue size to make sure it doesn't go too far. Actually, this is the cause of the issue. UQ size is not fixed at all. By default, it is 1024, like the list. But it can be changed by the guest. It is something that you can configure from the guest. You just have to write in the MMIO. You can change it to any value in 16 bits. So UQ size is actually, maximum is actually 0xFFFF. So if you go back to the descriptor chain, you can chain more than 1024 descriptors, and you can start writing the output segments outside of the buffer. So the function fails to properly check if there are too many descriptors in the list, and you end up with a out-of-band write after the VirtuBox structure, while you will write this function, this structure, out of band. As I said before, the VirtuBox structure can be located on the stack or on the heap, depending on the device you're using. So mostly VirtIO disk will allocate in the heap, and VirtIO network card place it on the stack. I decided to go with the stack buffer overflow exploit because it seems easier. And one big detail about the bug is that you will write out of band with chunks of 16 bytes because it's the size of the descriptor. But we only control 12 bytes of those because we fully control the GPA, it's okay, but the size is originally 4 bytes, and it's converted to 8 bytes. So the last 4 bytes will be padded with 0. Okay, let's exploit these bugs and steal the treasure and get some beers. So the bug in the VirtIO net card can be triggered from this function. I will not say its name either. We already defeated ISLR with the first bug, and VirtualBox is compiled with that stack canaries because performance issue. Why not? And so it's like easy win, like 101 stack buffer overflow, web gadget, shellcode, the win. Well, actually, no. This is a stack frame of the representation of the stack frame of the vulnerable function. As I just said, when we control 12 bytes out of the 16, we will write in out of bands. So on the left, there is all these green boxes where I can fully control the value. But on the right, I will only control half of it, the 32 upper bits. And as you can see, the saved return pointer is always located on the right, so I cannot fully control it. And if I overwrite it, it will be an invalid value and it will crash. So bad luck, but, and more of that, all the saved registers that are before in the stack frame, they are not interesting to control at all. They will be just popped again on the parent function, so there's nothing to do with those either. But fortunately, we still have some interesting things in this stack frame, and more particularly, we have these two objects called pdvins and pdcc, which are arguments to the function, and that are located thus after the saved registers. And both, if controlled, if we control perfectly the value, and we have some data at a known location we can use, we can, by corrupting them, we can get two arbitrary calls, one for each object. And those arbitrary calls will be done before the function returns. And after that, we cannot return from the function because to be able to override those, we have to override the saved pointer. And since we cannot control it correctly, it will crash. So the function cannot return, but we have two arbitrary calls. Not that much arbitrary because we are in Windows userland, and thus there is control flow guard. Control flow guard is a mitigation on Windows that will prevent you to jump anywhere from dynamic calls. So if you corrupt a vtable or some pointers like I'm doing, you can only call specific functions that are in the bitmap, and actually it's all the function of the binary. So you can call any function, but you cannot jump in the middle of a function. So we turn our stack buffer overflow into two arbitrary calls, and this function can never return. So the strategy we're using is to use the first arbitrary call to perform another corruption. In our case, it is an arbitrary write. And we use the second arbitrary call to call sleep with a pointer value as far as argument, so it will basically sleep forever. And so the function will never return, and we can use our other corruption with another thread to do something else. So we turn our stack buffer overflow into a single arbitrary write. We can only use it one time because now our vulnerable thread is sleeping forever. So we have a single arbitrary write. We have ASLR defeated, thanks to exploited leak. So most importantly, we know where the stack frame of the XHCI thread is. And this thread, so it's USB 3.0. It's handling the commands for the USB 3.0 controller. And when there is no command, the thread is sleeping on a semaphore. It's waiting to be woke up. And with the leak, we know where the stack frame is located. So the idea is to use the Virtual thread, vulnerable thread, to perform the first corruption, use the arbitrary write to overwrite the saved RIP on the stack frame of the other thread, and then the second call to sleep forever. And after that, we can just wake up the XHCI thread by sending a command, and it will jump on our web chain when trying to wake up. And this basically allows us to bypass control flow guard because control flow guard can only control dynamic calls. It cannot control the saved pointers on the stack. So from there, we can just do a web chain and jump on shellcode, and we got arbitrary code execution with medium privilege. I have a small demo video, even if it's not very interesting. At the time, it was the latest version, obviously, last year, and the exploit. So we have Ubuntu as a guest and Windows as a host. We just leak some pointers with the first bug, overwriting the stack thread, and get a calc on the host. Thank you. Yeah, let's get some beers. .2 to Vancouver 2024. So as I said before, the exploit was fully written in Python and compiled with pinstaller to have a single binary. It was 100% stable. There is nothing not deterministic in the exploit. And as we said before, we chained it with the Windows privilege escalation. So if you want to talk about it, Bruno is here. And we had a full win, very lucky because we are picked first in the draw. At Pontoon, if you're not picked first, you're likely to get less money. And we had no bug collisions, so we won like $90,000 for this project. And yeah, just to conclude, for us it was just a fast and fun project. It lasted a month in total for the VirtualBox part. I learned a lot about virtualization and could improve my tooling. And we'll say VirtualBox is already a great software, but it's also a great software to learn about VM escapes because you have a really easy code, open source code to read. Like it's not like the QEMU code; it's actually readable. And there's still lots of bugs to find apparently because last year when I did it, there was like I think 3 or 4 entries at Pontoon, and there is 6 this year, so it's getting trendy, and it's quite fun. So you should try it. And we also have an entry at Pontoon this year, so if you're interested, you can see us targeting VMware ESXi tomorrow at 2 p.m., something else in the difficulty of the target. And finally, if you want to learn about VM escapes, we have a training available seat, so you can have more details about it on our website, reversetactics.com. Thank you very much, and if you have any questions.
Are there any questions? Of course.
Hello, thanks for the talk, nice talk. My question is related to fuzzing. Do you also do some fuzzing on hypervisors? Or do you only do like manual analysis?
I do not. If you want to talk about fuzzing, I think you can talk to Sina Synology. He did that, I think, for his bug. I do not because for me it's quite difficult to implement this in hypervisors because you will very quickly trigger asserts and crashes of the virtual machine, but not actual bugs, like just asserts everywhere. But it's doable, of course, but I'm not a big fan of fuzzing generally, and for this kind of target, I like to do the manual review.
Okay, thank you.
Any more questions? All right, thank you for the talk, and thanks everybody for being here today.
Thank you very much.